Hello and welcome to York Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. To reach us on socials, you can always connect with us on Instagram with the handle @YorkUObservatory. Good evening, everyone, and welcome again. I'm Maheen, and I'll be one of your hosts this evening, along with Darius, Daniel, Dave, and Hector. We are here from the Alan I. Carswell Observatory at York University, and tonight we have got an exciting talk on the topic Alternative Biochemistries for Alien Life by York University student Boris Ciric, whom we will be introducing shortly. Before we continue, I would like to acknowledge that the observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Takaranto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. I will now hand it over to Daniel to start us off with some updates on what's up in the sky this week.
Thank you, Maheen. Welcome, everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week. This week, we will have the Golden Eye Cluster, also called the Pac-Man Cluster, and the Leo Triplet visible. While you can get away with just using a 10 by 50 pair of binoculars, they can only show you elongated patches of light. So to view these objects, you will require at least a 6-inch telescope. Lucky for us, the moon is in a waning crescent phase and will be a new moon soon, this Sunday. Right now, for local observers, we will have Uranus, Jupiter, and Mars visible. But the first two will be setting around 10 p.m., along with the Orion constellation, while the latter will remain up throughout the night. While Jupiter and Mars are visible with the naked eye, they will only appear as bright spots in our sky, but Uranus will be harder to look for. If you would like to better resolve these planets, a pair of binoculars and/or telescope will do the job. Now I'll hand it over to Dev, who will be introducing our speaker for tonight.
Thank you, Daniel. Hello, everyone. Today, I'll be introducing our speaker, Boris. Boris Ciric is pursuing a dual degree in astrophysics and atmospheric science at York University. Through collaborating with Professor Lee, Boris conducted research that analyzed astronomical images to measure air glow influence on light pollution. Boris is currently training to be certified on the 1-meter telescope at Alan I. Carswell Observatory. Boris also helps with the observatory outreach programs. Welcome, Boris.
Oh, let me just skip the screen share. So my presentation is on alternative chemistries for alien life. Thank you for tuning in. So a lot of the time when we talk about biochemistry, specifically biochemistry on Earth, we say that life is carbon-based. That might be something that you've heard in either scientific literature or even just like sci-fi a lot of the time kind of uses this topic as well. But what does carbon-based life actually mean? So what that means is when you look at the molecules that actually make up organic material and living things, carbon is the primary element that you see in a lot of them because it makes up a lot of the more complex molecules that make up life. In fact, about 45 to 50% of an average organism's biomass is strictly carbon. And we also say that it uses water as a solvent. We'll get into that a little bit later. But first, we need to understand why carbon is actually useful in the first place, why biochemistry actually uses carbon. So carbon has 4 valence electrons, and it's also rather light, and it can bind with itself very easily. So what carbon can actually do is it can bond with itself to form long chains, like you can see in this diagram of a lipid there. You see like carbon, 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 and that's also binding to hydrogen is a very common one. You can see it's also got some oxygen bonds. It can bond to a few other atoms as well. But basically what carbon can do is because it can form these long chains, it can form very big and very complex molecules. There's an entire field of chemistry specifically dedicated to these kinds of things called organic chemistry. And we have found like tens of millions of different organic compounds at this point. And most important ones for us are actually, once they get big enough, you can actually get to a point where certain molecules can encode information and self-replicate. So that's like DNA. That is something that can actually like encodes the genetic information of or organism. And there's also stuff like proteins, which also have their own function. Some of them can self-replicate, some of them can't. So really, when we're talking about like life, we're really talking about like what kind of processes, what kinds of different kinds of chemistry can form complex enough molecules that you can feasibly encode information on it, and then you can get some kind of life form. So there's a big caveat to this, which is complex chemistry is necessary for life, but it doesn't necessarily guarantee life. So there's a quote, actually, there's 2 quotes actually from 2 different chemists I like. One is named George Whitesides, where he said, it's a long wait from slime to Mozart. Slime basically being like the earliest life on Earth. It's a pseudonym for that. And it's basically saying it took a long time for life to get from there all the way to human civilization. But then there's another quote in response by Steve Benner, who is also a chemist, which is, it's a long way from HCN to slime. And basically what he's saying is, we see all these organic compounds that are really useful for life, but we don't know the entire process of how you get from an advanced molecule to an actual living thing. That's a lot of different chemical steps in there, and we don't know all of them yet. We've actually tried experiments in the past where we tried to create life just based on these basic materials. And so far, we've had no success in that. So there's definitely certain elements of the process that we don't understand yet. And that also limits how well we understand alternative possible chemistries as well, because maybe some of those chemistries are actually missing a step that would be needed to create life. So because of this is a very speculative topic, like I do recommend taking like some of this with a grain of salt. We don't know how much of this is actually possible, but based on our current understanding, some of this might be possible. So what we're looking at right now is some forms of advanced chemistry that are able to produce complex molecules might be at least a good starting point to bounce off of before we really get into the nitty-gritty of things. So what other elements could you feasibly use? The most common one that's been discussed is silicon-based life. This is also one that's used in a lot of science fiction. So if you look at silicon, silicon is in the same group as carbon. It's actually right below carbon on a periodic table, and that means that it also has 4 valence electrons, so it can feasibly bond with 4 atoms. It can also bond with itself to form chains, and these are actually called organosilicates. A lot of the time when you look at organosilicates, you actually do see some carbon mixed in that helps with the chain, but usually the basis is silicon. That's what it needs to be considered an organosilicate. This has actually been proposed a lot because of how similar silicon is to carbon. Silicon-based life might not actually be super different from carbon-based life, and in fact, it could actually potentially exist in environments that are more hostile that carbon-based life wouldn't be able to exist in. There are problems though. So a big one is because silicon is further down on the table, it is heavier than carbon, and the molecular bonds it makes are weaker. So it's a lot harder for it to make really long chains, like the kinds you need to make something akin to, say, DNA. It also is less stable in oxygenated atmospheres. So if you look at like, the Earth's atmosphere, there's a lot of oxygen. It's a bit hard to get that kind of big molecule with silicon because it's a lot more reactive. It also tends to be more stable in higher temperatures as well. So if silicon-based life were to exist, you probably see it in more of a high temperature, low oxygen environment. So say planets that are kind of like closer to their star. One interesting proposed region that silicon-based life could actually exist in is inside the mantles of planets because it's low in oxygen. You get those very high temperatures, so that would be interesting. And another big one as well is that because it's heavier, it also requires more energy for its reactions to actually form the bonds. So if you think about just the sheer number of chemical reactions that are happening inside of a living organism at any given time, even a simple organism like a cell, it's a lot of them, So if you think about it, like because silicon needs more energy for each and every one of those reactions, it's going to be a lot less efficient than carbon-based life. So let's say there was a situation where carbon-based life and silicon-based life both formed on the same planet. The carbon-based life could effectively outcompete the silicon-based life because everything the silicon-based life can do, the carbon can do, but with less energy. So it's a much more kind of advanced, kind of efficient organism. So likely, if silicon-based life did exist, it would most likely live in these kinds of conditions where carbon-based life actually would not be able to exist. There's also another interesting thing. This is why if you kind of look at group 14, these are ones that have 4 valence electrons. You'll see like we've got carbon, we've got silicon, but we've also got heavier elements. Like we've got germanium, we've got lead down here. But no one's ever really considered like say lead-based life. And that's because lead is so heavy that you're really never going to be able to get organo-leads. Like you're just in no kind of situation are you going to be able to get a chemistry, organic chemistry that's lead-based. So silicon is the one that's been most talked about. There have been a few other chemistries that have been proposed as well, like boron and nitrogen. These can actually combine to form large chains as well. This has a similar issue as silicon, where it is highly reactive with oxygen. But if you have a planet with a reducing atmosphere, reducing basically means an atmosphere with little to no oxygen, so it's not an oxygenating atmosphere. It could be stable enough to form large molecules. It also has a similar issue to silicon where like a lot of organoborons that you look at, if you look at their chemical structure, they do often include carbon as a little bit, but it is still kind of like a basis of boron, and that's why it's called an organoboron. A couple of other elements have also been proposed. One is metal oxides. So these can kind of form like little nanotubes or crystalline structures. And some people have proposed that maybe those could be used as an alternative for the kinds of molecules that we see in DNA. Like maybe those could actually encode genetic information as well. It would also be good in high temperature environments similar to silicon. There have been a couple of other elements as well, like sulfur is a big one that can also form long chains. The problem with sulfur, though, in addition to being reactive with oxygen, is it has 6 valence electrons instead of 4. So it can only form 2 bonds. So when sulfur forms these long chains, it only forms these long ones in one direction. It can't branch out like hydrocarbons can or organic chemistry. Arsenic is also an interesting one. So that, again, reactive with oxygen, but it's actually been proposed that maybe early life on Earth, like before the Great Oxygenation event, might have actually been able to use arsenic somewhere in its biochemistry. But then due to the Great Oxygenation event, like arsenic ended up not being useful anymore. So a lot of all that life would have effectively died out due to that. So we've talked about the chemistry that actually makes up the life forms, but there is actually a second factor to this, and that is all life on Earth needs water. Everywhere you find water on Earth, you find life. But why is water specifically so important to life on Earth? So to form life, you basically need some kind of solvent for the molecules to mix up in so that you can get those organic reactions. So you can get those chemical reactions that will eventually form life. And it turns out water is pretty much the best solvent that there is. And there's a couple of reasons for this. So one is its polarity. So you can see on its shape, it's kind of like it's got a bit of a dipole here where you've got the negatively charged oxygen, you've got positive charges. And that means that even though the whole atom is ultimately neutral, you still do get some electromagnetic attraction to these. So that can actually help like the positive and negative ions kind of like come together and form certain compounds. Water also has very low reactivity because it has a low energy of formation. So basically what that means is it's very unlikely to react with other things. So whatever chemical reaction is happening in there, water is going to stay out of it. It's not going to interfere with the reaction in any way. So because water is such a good solvent, it has been a little bit difficult to identify other options. But what a lot of people think is that as long as you've got some kind of fluid for the molecules to work in, and as long as that fluid isn't interacting too much with those compounds, there should be other forms that could work as well. So one big one is ammonia. Ammonia is just very common in the universe. It isn't polarized. It tends to be pretty reactive, which is a problem. But because it's so common in some areas, like some planets that are very far away from the star, you could possibly get liquid ammonia, and it might be able to work for certain chemistries. A big one actually is methane, because on Titan, which is Saturn's largest moon, you actually do get lakes of liquid methane around poles. So if methane does work as a fluid for organic chemistry to happen, then we could actually get some form of primitive life there. On the flip side, at higher temperatures, silicon dioxide might also work as a solvent. And still in cold environments, like let's say you go as far as something like Triton, which is one of Neptune's moons. Triton is actually so cold that it has liquid nitrogen. So liquid nitrogen might also work, or even liquid fluoride. And, we're only talking about like rocky planets here, but even on gas giants, actually, if you go deep enough into a gas giant's atmosphere, eventually the pressure is going to get to the point where instead of the atmosphere acting like a gas, it acts as something that's kind of like a mix of a gas and a liquid. We call it a supercritical fluid. And if you look at these supercritical fluids, like let's say on Jupiter, you get a lot of supercritical hydrogen. That could actually work as well as a fluid. So maybe like deep inside gas giants, if it's warm enough, then some kind of chemistry might be able to function there as well. So you kind of look at this stuff, right? And you think, okay, you need to kind of go to all these like weird and bizarre planets to be able to find some kind of alternative life, if alternative life exists. But it's actually entirely possible that we might not even need to leave the planet to find non-carbon-based life. There is this entire concept called a shadow biosphere, and a shadow biosphere is basically another biosphere that's living alongside our carbon-based one that uses a different chemistry or different processes that we have just never discovered. So you might think like, okay, how could we miss something like that if it's right on Earth? But there's a couple of reasons for it. So one big one, and this is actually a concept that worries a lot of people who work with astrobiology, is that life that's operating in under different chemistries might be completely unrecognizable as life to us. Like maybe we go to another planet, say like Europa or Titan, and we'd actually find life, but it would be so different to us that we wouldn't recognize it, and we just kind of like gloss over it. So maybe it exists and we just haven't really figured out its life yet because our definition of life is still a bit too limited. It might also live in places that are inaccessible to us where carbon-based life cannot survive. So earlier I mentioned that there was a proposal for silicon-based life where maybe it could exist inside planet mantles. So if it was something like that, then we wouldn't have really been able to see it because we've never actually dug down to the mantle before. It's too hot for our current technology. It could also have existed in the past but went extinct. So, I mentioned earlier that silicon-based life would probably get outcompeted by carbon-based life if they both existed in the same environment. And also, it has been proposed that arsenic biochemistry might have actually existed early on in Earth's existence as well. There's also lots of different experiments being done in terms of like how to form life and also which chemistries can form life, like actual physical experiments. So who knows, maybe at some point we might crack the code and we could actually figure out how to make some other alternative form of life entirely by ourselves instead of actually finding it first. And that's all. Thank you for tuning in.
All right, thank you so much, Boris, for a very informative and exciting talk. We do have some questions, so I'm gonna take it over from you. And then our first question is from Hector.
Hi, Boris. Thank you so much for such an interesting talk about all this chemistry behind astrobiology. I think it's really interesting. So yeah, thanks so much for sharing with us all this information. And I have a question for you. Well, are there any specific molecules that you think are more likely to be universal to all forms of life, regardless of their chemistry?
It would probably be hard to say if there's one that's like full on universal. I would say that the most common one probably would be carbon, just because whenever we look at different forms of chemistry, we do see that carbon does seem to be the best in terms of forming large molecules. And, even when I was talking about the organosilicons or organoborons, usually those molecules actually do have some carbon mixed into them. So I would say that carbon is still probably the most common thing. Perhaps carbon-based life would be the most common form of life, even if those other chemistries are possible.
Okay, all right, makes sense. Makes sense. Thanks so much, Boris.
And I think the next question is from Dave.
Yeah, my question is, what methods can be used to detect signs of alternative chemistries in exoplanetary atmospheres or surface conditions?
So when it comes to figuring out chemistries, when it comes to figuring out the chemistry of actually anything in space, what we use is spectroscopy, which is basically, if you don't know what spectroscopy is, light propagates as a wave and it can have different wavelengths. And when light passes through, say, a gas cloud or bounces off of an object, the object absorbs certain wavelengths of light, and which wavelengths of light it absorbs depends on its composition. And we found actually that each element has its own specific wavelengths that it absorbs, and we call that its spectral signature, just its spectra. So when we're trying to figure out the composition of things in space, we actually use spectroscopy to figure out what they're made of. So if we're trying to find signs of alternative chemistries, we basically look at their spectra and see what kind of elements and what kind of molecules are we actually seeing from the planet. And if we're seeing ones that normally we could only form, say, from biological processes, as far as we know, then that might be a good sign. Now, using it to detect alternative chemistries can be a bit trickier because we don't know 100% what all the biochemistries of that a life form would be, and maybe it could form some kind of other element that we're not another element, but it might have a different biosignature than carbon-based life. So it's definitely a lot harder to look for. Usually when we're looking for life on other planets, we're kind of comparing it. We're looking for Earth-like based life because other forms can be a bit harder to detect because we only have one data point for life. So spectroscopy and spectral readings, that would be the main thing.
Quite insightful. Thank you.
Hey, can you hear me?
Yep.
Sorry, I'm on a new mic. Okay, so my name's Darius. I'm a fourth year student in physics, and my question for you, Boris, is: are there any space missions or specific observing methods that we are currently employing to detect these different kinds of life that could exist?
So the Sorry, I didn't realize I was muted. The main observing method that we could be using would be the spectra. In terms of missions, there is a mission, I believe it's going to be planned to be launched in 2029. It's called the Ariel telescope. And it's basically going to take a survey of, I think something around 1,000 exoplanets is planned and trying to get spectral readings from them. And from there, we should be able to figure out if there's certain processes or certain readings that we get from their atmospheres that would imply some form of life living on that planet.
That's very interesting. I've been looking forward to that. Thank you for the great talk, Boris. That was very interesting.
So I also have a question. My question is that when looking for complex organic molecules as a potential marker for alternate forms of life, what kind of life or living organisms are we hoping to find on other planets?
So the coolest organisms would probably be complex organisms similar to us, but most likely the most common form of life would just be microbial life. Especially when you're talking about different forms of chemistry, it might have problems forming more advanced life, like it might only be able to form more simple life. It also depends on how hostile of an environment it is. Like simple life tends to be hardier than complex life. So if it's a very difficult environment for life in general to form in, maybe only microbial life could work. Another problem too, especially when you look at planets that are very cold, like let's say if there were life on Titan or Triton, because those environments are so low energy, if life did form in them, they would have very slow metabolisms. So if you look at like cells on Earth, like cells in your body might reproduce over the span of a day or so. Cells in that kind of environment, they might only reproduce once every couple hundred years. So because they're moving so slowly and reproducing so slowly, that kind of slows down the rate of evolution. So that would make it a lot harder for any kind of complex life to form, because even if it had the energy for it, it just might not have had enough time yet to actually form properly.
Great, that's quite interesting. Looking forward to the discoveries in the future. But there's also one more question by Daniel.
Yes. Hi, my name's Daniel, and I'm a fourth year astrophysics student. And my question for Boris is, what is a reducing atmosphere? It was mentioned in the boron and nitrogen slide. And I'm also wondering what planets are out there that have this sort of reducing atmosphere.
So usually when we're talking about reducing in a chemistry context, we basically say it's either oxidizing or reducing, and oxidizing, as its name implies, is caused by oxygen. So reducing atmosphere is basically an atmosphere that has little to no oxygen. So in terms of planets that are near us with reducing atmospheres, that's actually all of them. Like Earth is the only planet in the solar system that actually has a large amount of oxygen in its atmosphere. Like, and that's due to biological processes like photosynthesizing life is what put all of that oxygen into the atmosphere. So if you look at Mars, you look at Venus, like those are effectively reducing atmospheres because there's very little oxygen in them.
All right. Thank you for clearing that up for me. And I'll send it to Hector, who's going to wrap it all up.
Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening were Mahin, Darius, Dev, Daniel, and myself, Victor. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. All of our programs are free. But if you would like to make a donation, see our website at yorku.ca/science/observatory. You can always connect with us on Twitter with the handle @observatory and check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory/. Thanks for tuning in. Clear skies and have an excellent night.